remind you, last Thursday, we finished with a nice result about how to use transformations to give an effective condition for checking whether a quadrilateral is a parallelogram. Okay? This is, I emphasize this as kind of the first example that we've seen where this machinery that we're developing, transformation geometry, is useful in deducing things about classical geometry. Okay, so let's continue our study of translations and note some more nice properties that translations have. Particularly, we have the following theorem. A translation is a collineation. And there's more to this, actually. That satisfies for a line L, a translation, let's call this alpha. Okay? So a translation alpha is a collineation that satisfies for a given line L, for any line L. L is parallel to its own image. Okay? So this is a nice feature. Now notice that any collineation takes a pair of parallel lines to parallel lines. But here we're saying more. We're saying that the image of a line is parallel to the original line. Okay? So, let's prove this. So, first of all, we know that iota is a collineation. So, let's assume that we have some translation which is not the identity. Okay? So, assume tau sub p comma q is not the identity. And has equation given by tau of p comma q, tau sub p comma q of x comma y is just equal to x plus h comma y plus k. Remember that to specify a translation, we just have to specify these two numbers, h and k. Okay? Which of course means, or I should say meaning that, another way to write this translation tau sub p comma q is to just say that it's the translation between the points, the origin and some other point r, with r having coordinates h comma k. Right? Then of course we have the line specified by P and Q is parallel to the line specified by the origin and R. Okay, so what do we need to do in order to check that tau is a collineation? What's our procedure for showing this?
Find the image line.
Yeah, we take an arbitrary line and try to write down the image of that line under tau. Okay? So, we consider the generic line ax plus by plus c equal to 0. And set, okay, this was a big part of the homework last week. It's the same procedure. We set u equal to x plus h, and v equal to y plus k, which, of course, solving for x and y just gives us x is equal to u minus h, and y is equal to v minus k. And plug these in. Into our line equation. To get a u minus h plus b times v minus k. C is equal to 0. Of course, just rearranging this, put it in a standard recognizable form. Okay. What do we get here? We get AU plus BV plus C minus AH minus BK is equal to 0. So the image is the line with equation A capital X plus B capital Y plus C minus AH minus BK is equal to 0. Okay, so this is a collineation, right? Because we've now deduced the equation of the image of our generic line ax plus by plus c. Now, how do I verify the second part of this theorem? That L and alpha of L are in fact parallel.
Here are slopes.
Yeah, let's compare their slopes, right? What's the slope of this line?
Negative
Yes, good. Both lines, by which I mean L and alpha of L, have slope negative A divided by B. Implies that they're parallel. Okay, so this is in fact such a nice property that we give this type of transformation a name. a collineation, alpha, it is called a dilation. If and only if, for any line L, we have L parallel to alpha of L. Okay, so in other words, this theorem that we just proved is just saying that every translation is a dilation. Right? No. There are, of course, there are collineations which are not dilations. Can anybody tell me an example of such a?
Rotation.
Yeah, we can have rotation by
Subangle.
some angle. Yeah, 90 degrees, why not? Good. Yeah. For example, if rho is rotation by 90 degrees, yeah. For example, this is a collineation that is not a dilation. Okay. So, I was reviewing the practice exam, and I realized I should probably say the following. And we've kind of touched this fact that I'm about to say, but I want to emphasize it because it's important. Okay, so translation moves every point the same distance in the same direction. That is to say, the vector A comma B completely determines the translation. Okay? So, yeah, we basically said this. I just wanted to have emphasized that this is just a different set of terminology.
I have another question.
Yes.
It's related to the exam and also the proof you just did. Do you ever go over in class why a collineation reserves parallel lines?
No. No, we didn't.
Can you use in that proof right then? We just talked about it in that proof right there. I wasn't sure.
Yeah, we haven't proved.
Okay.
That's a good point. Maybe I'll do that for homework. Okay, it's a good exercise. Good. Okay. The vector AB completely determines tau given by this equation. Okay. In the computation that we made in the last proof, there's a little something more that we can deduce. Okay? So, let me just say furthermore. Given L with equation ax plus by plus c equal to 0, we computed that alpha of L has equation let me call this, change the notation here, and this, now my translation is tau sub p comma q. Okay, just so we have concrete points to work with in our notation. Right, so we computed that the image of this line L has equation ax plus by plus c minus ah minus bk equal to 0. So this allows us to give a necessary and sufficient condition for when a line is taken to itself.
Oh, yes.
So what is the condition here?
H equals BK.
Yeah.
Or equals, yeah.
Right, so let's write that out. Therefore, L and tau sub p comma q of L are the same exact line if and only if we have C is equal to C minus AH minus BK, which of course is the case if and only if AH plus BK is equal to 0. Okay, so now let's take this another step further. Let's consider the line from the origin to point R, where, just as in the notation from the theorem, R is just the point H comma K. Okay? Has equation HY plus, I'm sorry. I should write it this way instead. Y is equal to K divided by H X. Right? So we have this point, which makes a vector from the origin. And that vector, if we take the line that it lies on, it has slope K over H, right? So that's where this equation comes from. And of course, by arithmetic, we get something that we can usefully combine with our first bullet point. Sorry, my markers are not very good today. Try this one. Okay, so of course, this last equation is the case if and only if we have hy minus kx equal to 0, to put it in standard form. Okay? So, then we know that our original line L is parallel to the line defined by the origin and point R. If and only if negative a over b is equal to kh, right? Because we're using this line L of ours that has slope negative a divided by b. And that's the condition for them to be parallel, is that they have equal slope. Okay? So, this of course is the case if and only if h plus bk is equal to 0. Which is just the condition that we wrote down before. Okay.
Oh. So they're parallel to the same line.
Good. Therefore, our conclusion is that tau sub p comma q of L is equal to L if and only if L is parallel to the line defined by PQ. Okay? So, putting that all together, what we're saying is all the lines that are parallel to the line defined by PQ are fixed by the translation tau sub p comma q. Okay, so really quickly, here's the definition. A transformation alpha fixes a point T if and only if alpha P is equal to P. Okay, kind of an obvious definition, just wanted to be completely clear about the terminology that we're using. Okay, furthermore, you can talk about a transformation fixing any set. Okay, so let's say alpha fixes a line. L, if and only if alpha of L is equal to L. Now, there's a subtlety here, right? When I say alpha fixes a line,
It's not the same points.
it doesn't mean that it fixes the points on that line. It can move them around in the line. Okay? It's just that, or hence the word dilation.
Yeah.
Things can get spread out. Okay? So,
Relative would be iota every time.
right.
Which means this doesn't apply to iota, right? Because you don't have a constant parallel. Well, not directly into itself.
So, so iota fixes everything, right?
Right.
So, it does apply.
Wait. But like,
Not
the
any
parallel doesn't apply
facts.
more than
I'm sorry.
It's not an interesting fact.
Just not an interesting
It's
sense.
like trivially parallel.
It's trivial, exactly. Good. Okay, and I'll just say this anyway. In general, alpha fixes a set S if and only if alpha of S is equal to S. Okay? So then, let me recap the last thing that we proved. The translation tau sub p comma q fixes all lines parallel to the line that P and Q lie on.
And only those lines.
Yes. Right, and only those lines. Why is that? Because every implication that we made in this deduction was an if and only if. Okay? Good. And no others. Okay, that's what we proved. Okay? Furthermore, I shouldn't have put that box yet. Furthermore, tau sub p comma q fixes no points. Yes?
Unless it's added.
Unless it's added, yeah. Sure, let's just say exactly that. Unless tau sub p comma q is equal to iota. Okay. So, set of all dilations forms a group. Okay, so again, what do we have to verify in order to show that the set of all dilations forms a group? The four properties. And as was discussed in the homework, and we talked about it in class a little bit, every set of transformations satisfies the associative property, right? So we don't have to worry about that.
Also, we know iota is a translation, therefore addition.
That's right. Very good. Okay. So let's just say, let's denote this. Denoted script D. Okay. So, all sets of transformations have associative property. Good. And then as Zach was saying, iota is a translation, which implies dilation. So, identity property, identity property checks out. Okay, now how about the existence of inverses? If I take an arbitrary dilation and find its inverse, how do I know that's a dilation?
It should also preserve slope.
Yeah, that's what we want. So this basically boils down to the fact that if L is parallel to L prime, then we necessarily have L prime is parallel to L, right? The fact that
You have to prove the existence of the
of
pre-image.
prove the existence of the pre-image. Can you elaborate on that?
Like we did before, we can't say that it can be inverted unless we can find one that maps to, right? Or the reverse.
Well, just to construct the inverse of some dilation, we know that's a transformation, right?
Yeah.
So
We'll say that for that. So, okay.
yeah, so we know an inverse exists
This is transformation.
because it's a transformation. We just have to check that it takes a line to a parallel line. Okay? So therefore, for dilation alpha, if L is parallel to, then we know alpha inverse of alpha of L is parallel to alpha of L, right? That's because this is just L. I just flipped the, this is to say the relation of being parallel is reflexive, okay? Which is a weird point to talk so much about, but it's kind of important. Okay, so G, D has a inverse property. Okay. Now, what about closure? So for closure, if we take two parallel lines, L and L prime, and a third line, which is parallel to L prime, L double prime, then we must have L is parallel to L prime. Double prime, yeah, same. Yeah, that is to say, the relation of being parallel is transitive. Okay? And of course, if you want to look at this analytically, these two have the same slope, these two have the same slope, therefore, the first and the third have to have the same slope.
Almost an equality.
Sorry?
Almost an equality.
Almost, yeah. Okay. So dilations alpha and beta imply that beta composed with alpha is also a dilation. So we have the closure property. Okay. So additionally, the set of all translations forms a group, which will denote script T. Okay? So, let me just say now, instead of doing this together, I'll ask you to verify that this is a group for homework. And it's a fairly routine calculation, just like what we did for dilations. So, homework. Verify T is a group. And then I'll also ask, is T a subgroup of D? Okay, just a little practice staying comfortable with the basic definitions of group theory. Okay, actually, this is, I want to say more here. This is good. Show also that T is abelian. Okay? Which, if you think about it intuitively, it certainly makes a type of sense that if I shift all my points by some vector and then another one, I could.
Vector addition. Oh.
Okay? So this is a great exercise. Think about this. And try to write it out formally. We'll discuss that tomorrow. I assume this will be of interest. I'm definitely going to do this tomorrow, but I want you to try it on your own. Okay? Good. So, with that, the past couple lectures, what we've been doing is taking these familiar seeming transformations that we have an intuition for, and then writing down an analytic formula for them, and deducing the properties that they possess, these nice relationships. So now we're going to start down the road of doing a similar thing for rotations. I want to write down an analytic formula and then deduce the properties that these types of transformations possess. Okay? And to do that, we're going to start with a very simple type of rotation called half turn. Okay? So, what is a half turn? A half turn is a rotation that is an involution. Okay. So, in other words, what kind of rotation, when you do it twice, gets you back to where you started?
Degrees.
Yeah, exactly. In other words, that is a half turn is a rotation of 180 degrees about some point. Okay, so don't be intimidated by all the terminology that we've introduced. This is actually a very easy to understand thing. Okay? So, equationally, if we take the point P, A comma B, then a half turn about P has the following form. All right, sigma sub P of x comma y is equal to, okay, any guesses on how to describe this analytically? Okay, if you don't,
Minus 2, a minus 2x. Or like that,
very close. Negative x plus 2a
oh,
a negative y
d plot.
plus 2p. Very close. Okay, where does this come from? Well, where it comes from is we consider the point A, which is x comma y, and rotate by 180 degrees about P to get A prime, which is, we'll just call x prime y prime. Then the point P is the midpoint of the line segment between A and A prime. Right? So, in other words, P, and then I have some point A. If I rotate this 180 degrees around P, I get this point A prime, which is equal to sigma sub P. Okay. Right? So, how do we compute the coordinates of the midpoint?
Linear average.
Yeah. Linear average was what was said for people on Zoom. Probably didn't hear that. But yeah. So if we want to calculate the coordinates of this midpoint in terms of x, y, x prime, and y prime, then, so I'll say analytically, have A, the first coordinate, or our midpoint, is the average of the x components of A and A prime. That is x prime plus x over 2, and B is equal to y prime plus y over 2. Now it becomes clear where this formula comes from, right? We'll solve these for x prime and y prime to get x prime is negative x plus 2a, and y prime is negative y plus 2b. Okay? I'm really sorry about this, but I'm going to try to use blue. And if people on Zoom can't read that well, let me know right away. I don't know why I'm so unprepared there. Okay, so let me ask you. Notice that the transformation, the half turn, sigma sub p, doesn't tell you anything about how you get from A to A prime. The way that one point moves to another is not encoded in this. Okay? That's a question that more properly belongs to differential geometry. Actually, parameterize a path.
Does it technically care?
No.
Because if I'm saying it has to go along the path of other rotations, would it have intermediate if it's like a continuous transformation?
Right. So, we talk about how a transformation takes a point to another point. That's just a metaphor that's useful to us. There's no motion actually happening. Okay?
Just a mapping.
It's just a mapping.
It's not the set of transformations.
Yeah. So I just wanted to point that out. Don't be fooled into thinking that this tells you like a path through the plane. Okay? So let's characterize what's so nice about these types of transformations, half turns. How does that come out? Great. Okay, so a half turn is an involuntary, by which I mean it's an involution. It's an involuntary dilation. What else can we say about it? The midpoint between some point A and the image of A under a half turn is P. Okay? We've already shown these two things. I'm just recording what we've done, right? This is how we derived the formula for a half turn. Okay? Now, furthermore, a half turn sigma sub p fixes the point A if and only if Okay, and then furthermore, sigma sub p fixes the line L if and only if the point P lies on the line L. Okay? So, okay. So, let's prove these things. First, let's prove that sigma sub p is an involution. Okay? So, that is to say, let's let p have coordinates h comma k. And let's take be our input point, x comma y. Then sigma sub p of a is just equal to sigma sub p of negative x plus 2h comma negative y plus 2k, which is just equal to, sorry, negative x plus 2h plus 2h comma negative y plus 2k plus 2k, which of course is just a. Okay. So, let's see. Fixed point P. Okay, so let's suppose that sigma sub p of a is equal to a. Then put another way, this means that negative x plus 2h comma negative y plus 2k is equal to x comma y. This is the case if and only if we look at each of these equations separately, right? 2h equals x and negative y plus 2k equals y. Solve these for x and y, and you get x is equal to h and y is equal to k. If and only if x is equal to h and y is equal to k. So, therefore, k was in fact p all along. Okay. Now, let's discuss be a dilation. What do we do here? It's the same thing that we've been doing for all the times we verified a collineation or a dilation. We take the generic equation of a line, right? So consider line with equation ax plus by plus c is equal to 0. Then the image under sigma sub p this line is found by, well, the same thing we've been doing since last week. We'll set u be equal to the output of sigma sub p, right? Negative x plus 2h, and v equal to negative y plus 2k. And solve both of these for x and y. Okay, so this gives us x is equal to negative u plus 2h. And y is equal to negative v plus 2k. And then we just plug that into our equation for the line. So we get a times negative u plus 2h plus b times negative v plus 2k plus c equal to 0. Okay, so we rearrange this. What do we get? We get negative almost skipped ahead there. Negative AU minus BV plus C plus 2AH plus 2BK. So now this formal thing where we put the variables back in, right? So image line has equation negative AX minus BY plus C plus 2AH plus 2BK equal to 0. Should have said that here too. Now, so okay, what we've done is shown that sigma sub p is a collineation. Right? We started with a line here, and we got back an equation of a line in the image.
Right.
Okay. Now, if I want it to be a dilation, what's the additional condition that I have to satisfy? Yeah, the image line has to be parallel to our original line. But clearly that's the case here, right? Right, so sigma sub p is a collineation. And in fact, is a dilation. Since the image line has the same slope as our first line. Of course, that was ax plus by plus c is equal to 0. Okay? So, let's now discuss fixed lines L for sigma sub p. Right? So this is a little clever. Okay, so we have an equation for the image of an arbitrary line. I'm going to write this in a somewhat unusual way. Okay, so let's rewrite the equation of the image line. So first of all, I can scale this by -1. I can multiply -1 through by both sides, to both sides of this equation, right? That leaves it unchanged because I have a 0 on this side. You can multiply the equation of a line by any number and you get that same line. It's just an alternate form of the equation, the same line, okay? So first, I just want to say that another way to write this equation is as follows. Okay, so I'm going to keep rearranging this a little. What I'm going to do is I'm going to add and subtract another copy of C. Okay, so ax plus by plus c, there's my added in copy, minus 2c, that's my subtracted copy, plus 2ah plus 2bk. Now, just factor a 2 out of that last constant term. So I got ax plus by plus c minus 2 times c plus ah plus bk. Now, why am I doing this?
Because that's our original one.
Yeah, these first 3 terms constitute the original equation that we started with of our arbitrary line.
That bit has to be 0.
Exactly. So in other words, in order for line L with this standard equation, in order for that line to be fixed, that last term has to be equal to 0. So I'll say that all again. That is to say, in order for line L with equation ax plus by plus c is equal to 0 to be fixed, that is to say, sigma sub p of L is equal to L. then we must have this last term, negative 2 times C plus AH plus BK is equal to 0. Now, you'll notice that this portion of my expression is again just the original equation of our line evaluated at the point h comma k. That's the part in the bracket is the original equation for L evaluated at the point P equals h comma k. So what does that mean? If I must have this be 0, I evaluated my line on that point, and it satisfies the equation. That means that P lies on L. Okay? Therefore, P lies on the line L. Okay, so, whenever I go over a proof like this, I would have never thought to that just adding in and subtracting the same quantity, but it turns out to be useful so often. So yeah, I'm always impressed by this kind of thing. So, okay. So these are nice transformations, these half turns. Okay, let's see what can be said. So let's take our investigation a step further. What can be said about the product of two arbitrary half turns? And why do I phrase this way? Is because we talked about what happens when you take the product of a half turn with itself. What if we just take two arbitrary half turns?
Just look different things.
Yep, half turns around different points. Exactly. Those are the only things that could distinguish two half turns, right? It's the same amount of degrees for every half turn. It's just the point that you're rotating about. Okay? So, let's let P be equal to A comma B and Q be equal to C comma D. And let us explicitly calculate the product of two half turns, one about P and one about Q, and evaluate that on an arbitrary point, x comma y. Then, if we take sigma sub q times sigma sub p of x comma y, what do we get? Well, you get sigma sub q of negative x plus 2a comma negative y plus 2b we apply sigma sub q, and we get negative x plus 2a plus 2c, comma, negative y plus 2b plus 2d. Okay? Which, of course, what does this give us? I'll just clean it up a little bit. That's essentially the heart of it. We got x plus 2 times c minus a, and y plus 2 times d minus b. Now, what does this remind you of?
This is a translation.
This is a translation. This is just a translation, right? Remember, the general form for a translation is x plus a, comma, y plus b. This is the formula. Here my a is 2c minus a, and my b is 2d minus b. This is just a translation.
This should be true for any even number of factors, right?
Yeah.
Because we flip the sign there.
Yeah. So you're actually going to do something very similar to that tonight as part of the homework assignment. Good observation. Okay. So let's see here. Here's the theorem. This will get going in that direction. Okay? So if Q is the midpoint between points P and R, then what we can say is that sigma sub q times sigma sub p is equal to tau of sub p comma r, which is equal to sigma sub r times sigma sub q. Okay? Okay, so here's the proof of this fact. Let's evaluate the left-hand side of this, sigma sub q times sigma sub p on the point P. And what do we get? Well, by our first theorem on half turns, sigma sub p of p is just p. It's the only fixed point of sigma sub p, right? Okay, so we get sigma sub q of p. Now, what is sigma sub q of p? R, yeah. Sigma sub q of p is r because I chose q to be the midpoint between p and r. So when I do a half turn, I take p onto r. Okay? That's just from the characterization of what a half turn is. That's one of the first 3 different ways I wrote down what a half turn is. Okay? Okay? Good. Now, let's look at the far right-hand side of my string of equalities here. And here I have sigma sub r times sigma sub q. And we'll evaluate p on that. Okay, so again, by the same reasoning as before, sigma sub q of p is just r. minus sigma sub r. Okay. Now, I guess I should write this on the next board. Try to save space, but I don't want to be confusing. Okay, so we just showed that the product of two arbitrary half-turns must be a translation, right? So that is to say, both the far left and the far right are translations. And what do we know about translations that take a given point to another point? For any two distinct points, there is a unique translation that takes one to the other. Okay? So, let me write all that down. We know that sigma q, sigma p, and sigma r, sigma q must be translations. And there is a unique translation taking P to R, right? Therefore, these two translations have to be the same. And we know this translation takes P to R. Okay? So therefore, we get R equalities. Oops. E R. Get out of here. Sigma sub R, sigma sub Q. Okay. So, here's some other problems. And then remember I asked you to verify that the set of translations is a group. Okay? So don't forget, tomorrow evening after class, I will send out the solutions to the practice test. Okay? And so yeah. So we'll discuss the homework at the beginning of class tomorrow, and then at the beginning of class on Wednesday, the day before the exam, bring questions from the practice test. We can go over it together. Okay. All right, I think let's just call it a day then. It's a long time to lecture. And you know, like I'm being active. Like it must be even worse for you guys.
Most of our class sections are like, we know, like we've known for decades that psychologically it's like maybe you should stop for 50 minutes. No.
Yeah,
No.
That's academia for you.
Right, Rosen.
Yep.
Thank you.
Mm-hmm.
See you.
See you.